In this tutorial, I will talk about two topics. The first is the parametric representation. The second is how to calculate the arc length. Okay. First, the parametric representation. So here's example 1. There are 2 points A, B. For A, the coordinate are -1, 0, and for B, the coordinate are 1, 0. There are 2 points on the xy plane. So here the question is, find a point P on this circle which minimize the value of PA squared plus PB squared. Okay, for this question, so first think about how to represent the point on this circle. Okay, so give the parametric representation for the point on this circle. So here we can see that this circle centered at point 3, 4, and the radius is the square root of 4, which is equal to 2. So in general, let's say in general, if the circle is expressing this equation, so here this circle means this circle centered at point A, B, and with radius r. Okay, here this is the parametric representation for the point on this circle. Here we can see for x equal to a plus r cosine t. For y equals to b plus r sine t. R is the radius, a is the x coordinate for the center. Okay, b is the y coordinate for the center. Here the cosine t, sine t. What's the geometric meaning of t? Okay. Let's say in this figure, you can see that this circle centered at a, b, and with radius r. Then for any point here, let's say it's x, y on this circle. If we let this angle, okay, this angle is the angle between this line and x-axis. Okay, if this angle is t, then we can see that since this length is r, we know that this height is r sine t. Therefore, for this point, the y coordinate equals b here plus r sine t. Similarly, for x, okay, here the length, this length equals to r cosine t equals to this length. Therefore, the x coordinate is a plus r cosine t. Okay. So, okay, this is the standard parametric representation for the point on this circle. And we also know the geometric meaning of here the parameter t. Okay. So in general, for a curve or for a circle or for ellipse, there could be many parametric representation, but some parametric representation is good, some is not. So here the good means it's easy to interpret the geometric meaning of the parameter. Or after this parametric representation, it helps us to solve the problem. Okay. But here for this representation, which is a standard parametric representation for a circle. So make sure you understand this. Okay, back to the question. So here the question is how to minimize the value of PA squared plus PB squared. After representing the point on this circle parametrically, the next question is how to express the value of PA squared plus PB squared. Okay, let's assume the bed point. So let's say point P is 3 plus 2 cosine t, comma 4 plus 2 sine t. Then it's easily to calculate the PA squared plus PB squared, right? The challenge part is how to minimize it. If you do this calculation, you will find in the end you need to calculate the value in this form. So you will see that in the end you need to calculate some constant plus something like this. Here the t is the parametric, the parameter in the parameter representation. Okay, here for some constant a and b. Okay, now the question becomes how to get the minimum value of the function like this. Okay, of course you can treat this as the function of t, and you can, let's say, calculate the derivative of this function with respect to t, and let the first order derivative equals 0, and get the value of t. Also do the second order derivative to verify, to see whether it's a minimum value or maximum value. Okay, but there are simpler way to find the maximum or maximum value of the function in this form. The way we do it is convert it into the form something like a sine t plus alpha. The question is what's the value of a and what's the angle alpha? How these two values be represented in terms of a and b. Okay. You must have seen this equation before, like the sine alpha cosine t plus cosine alpha sine t equals sine t plus alpha. Okay, here we also use the identity that sine alpha squared plus cosine alpha squared equals 1. Then back to this form, we can see that it is equal to square root of a squared plus b squared times a over square root of a squared plus b squared sine t plus b over square root of a squared plus b squared. Easy to verify that this square plus this square equals 1. Therefore, we can treat this, for example, as a sine function of theta. Here, this is the cosine function of angle. Let's say in this case, we call it alpha. Okay, we let this equals sine alpha, we let this equals cosine alpha. Then use this equality. We get that a equals square root of a squared plus b squared. And for alpha, this is sine alpha, this is cosine alpha. Therefore, the alpha is arctangent a over b. Okay, in fact, it's this term over this term, but the square root of a squared plus b squared cancel out. Then, after converting the original function of t into this form, it's easy to get minimum value or maximum value of it, because the range of sine t plus alpha negative 1 to 1. Therefore, for this function of t, the maximum value is square root of a squared plus b squared. The minimum value of it is negative square root of a squared plus b squared. Okay, here, because in this question, there's no constraint on the parameter t. And in the exercise 1, here the constraint for x and y are that both x and y are larger than or equal to 0. Therefore, there will be some constraint on the parameter t. But again, if you know the domain of sine function, you can figure out the range of that function. After finding the minimum value of pa squared plus b squared, the last part is find the corresponding point p. As I mentioned, the tangent alpha equals a over b. Therefore, we can get the value of alpha, and we know that when t plus alpha, let's say, equals pi over 2, then the sine t plus alpha gets the maximum value. Or when t plus alpha equals negative pi over 2 plus the multiple of 2 pi, then we get the minimum value of sine t plus alpha. Therefore, we can get the corresponding t given that we already know the value of alpha. If we know the value of t, then we know which point p is. As I mentioned, for the exercise 1, this question is we use the same method, but it's more complicated because there's some constraint on x and y. Therefore, we need some careful calculation to find the minimum and maximum value. Okay, let's move on to the example 2. As I mentioned, if it's a good parametric representation, then the parameter, it's better that the parameter has geometric meaning. Also, if you know the geometric meaning of that parameter, it's also easy to memorize what's the, let's say, standard parametric representation for some curve, for the ellipse, sphere. Okay, let's say in this example, ellipse. And what's the parametric representation for the ellipse? So in fact, we use the identity that cosine alpha square, let's say cosine t square plus sine t square equals 1. Then we know that for the ellipse, the parametric representation is x0 plus a cosine t, and the y coordinate is y0 plus b sine t. Then you may ask, what's the geometric meaning of that t? Okay. Let's say first we draw a circle, let's say centered at 0, with parameter b here, b as 3. Okay, also we draw a circle centered as origin. So here in this case, x0 and y0 both equal to 0. Okay, and then there's a straight line which intersect with the small circle and the larger circle at the point P1 and P2. Okay, let's say this angle is alpha or t. Okay, let's say in this figure it's alpha. Okay, let's say there's another straight line which passes through the P2 and also perpendicular to the x-axis. Okay, this straight line is perpendicular to the x-axis, and so there's another line which passes through P1 and it's perpendicular to y-axis. Okay, and the intersection of these two straight lines is P. Okay, then the question is what's the coordinate for what are the coordinates for P? Okay, let's see the x coordinate. Okay, so for the x coordinate of P equals the x coordinate of P2. Remember, we just talked about the parametric representation for a circle. We know that the x coordinate for P2 is, let's say, a cosine alpha, which means the x coordinate for P equals a cosine alpha. Then let's see what's the y coordinate. The y coordinate of P equals the y coordinate of P1. Okay, and for this small circle, the y coordinate of P1 equals to b is the radius of it, b times sine alpha. B sine alpha is the height, the y coordinate, which means for P1, the y coordinate is b sine alpha. Therefore, the y coordinate for P is also b sine alpha. And we can see that the coordinates for P are a cosine alpha, b sine alpha. Okay, let's say we rotate this straight line counterclockwise, then the locus of P is the ellipse. Okay, here a equals the radius of the large circle and b equals the radius of the small circle. We can see that here the parametric for ellipse is, we call it alpha. The geometric meaning of alpha is here, this angle. Here this is the parametric representation for the point on the ellipse. It's a sine alpha, y equals b sine alpha. And we also talk about the geometric meaning. And next, sphere. Okay. First, let's see what's the parametric representation. Here x equals r cosine theta sine phi, y equals r sine theta sine phi, z equals to r cosine phi. Looks complicated, but as I said, if you know the geometric meaning of theta and phi, it's very easy to memorize these three equations. Okay, let's see. There's a sphere. There's a point. Let's say there's a point P on this sphere, and there's a straight line passes through origin and P. Okay, let's say the theta is the angle between z-axis and the straight line. Then the question is, what's the z coordinate for this point? It's like the r cosine phi, right? R cosine phi is like the height. This value is the z coordinate of this point P. Okay, then we know. Okay, we know the z coordinate. And what? Then let's see the x coordinate and the y coordinate. Let's say, imagine there's a plane which is parallel to the xy plane, and the intersection of that plane and the sphere is a circle. Okay. And the question is, what's the radius of this circle? It's like r sine phi. R sine phi is the radius of this circle. Then let's see. Then let's say the geometric meaning of this theta is. Then back to the circle in the xy plane. Let's say this is theta. Okay, and we know the radius. Here the radius is r sine phi. And let's say this is theta. Theta is the projection of this line, the angle between the projection of this line in the xy plane and the x coordinate. And this angle we call theta. And we know that the x coordinate is, let's treat it this way. The radius is r sine phi and times cosine theta. And for y, also the radius is r. The radius for that circle is r sine phi and times sine theta. Okay. So first the height. Height is r cosine phi. We get z coordinate. Next, okay, we get the radius. We get a circle. The radius is r sine phi. R sine phi times cosine theta is the x coordinate for the for presenting that circle parametrically, and y equals r sine theta, the radius times sine theta. Okay, now we know what's the parametric representation for the sphere. We know, and we also know the geometric meaning of these two parameters. So let's say this, the third example is a straight line. So for a straight line, there are many parametric representation, and you will see several parametric representation in this course. But here, for this example, the way to represent this line parametrically helps to solve the exercise 2. And here, I will not talk about the details of the parametric representation for this line. The idea is that consider that the geometric meaning of that parameter t, let's we call it t, is the distance between the point on this line and P. Okay. Of course, the P is passed through by this line, right? Let's imagine there's another point Q. Let's say the length of PQ, that line segment, the length equals T. Then think about how to represent this straight line. Okay, in terms of T. Okay. T is the distance. And if you figure it out, very easy to solve the exercise 2. Okay. Also for the hyperbola, or parabola, there are also some standard parametric representation for these two curves. As you may notice that, so there are lots of resources online, either the Wikipedia or the Wolfram. So there are many resources online. So make sure you know how to search, how to find the answer to your mathematics question. So for the example 3, so let's say for all the previous example, we convert the standard form to represent a curve to the parametric representation for that curve. So for this example, we do it in the opposite direction. So given that we know the parametric representation for the point, then what's the standard equation to represent that curve? So let's say in this example, so A and B, we're given the coordinate for A and B. And the question is asked, what's the locus of the midpoint for A and B? Now, two steps. The first is how to get midpoint of A and B. That's an easy one. But given that point, so we know that for both the x coordinate and the y coordinate, it's expressed in terms of theta. Yeah. Then how to convert that parametric representation in terms of theta to the equation. Okay. So that part is tricky, so it's different for different examples. But the point is, you need to cancel out that parameter, cancel out theta in this case. Let's think about it. So the answer is, so first we know that the A is an ellipse, right? So B also represent a point of an ellipse, and the answer for this question is also an ellipse. Okay. Okay, also exercise 4 is left for homework. That's a little bit challenging. Let's think about it. The second part is arc length. So in the lecture, we discussed about how to calculate the arc length given you know the parametric representation for that curve. So remember the arc length equals to the definite integral from, let's say, t1 to t2 square root of dxt over dt squared plus dyt over dt squared and dt. Okay. But if the curve is given as in this form, let's say y equals fx, then this is how you calculate the arc length. Here I won't go through the details for this example or exercise. In general, there are two steps. So first, determine which form we want to use. Okay, so using different form, you will find that the difficulty to calculate the integral is different. But which one you should choose, or either it's determined by the question. So, for example, in exercise 5, you are forced to calculate the arc length using the function in this form. So you have to use this equation to calculate the arc length. But what if you can do it? You have the freedom to do it, and which form you choose mainly depends on your experience. More exercise will help you to decide which one is the easiest one. that, you need to determine the upper limit and the lower limit for this indefinite integral. So in some cases, it's not a question, not a problem. So for example, in the example 4, you calculate the arc length in the form that x equals gy. Okay, and you're also given the domain for y. Okay, y is larger than or equal to 1 and less than or equal to 4. But how about if in the question you are just given the domain of x? Let's say x is larger than or equal to 1 and smaller than or equal to 4. But you do the integration respect to y, right? Then you need to do one more step to calculate the upper limit and lower limit for this integral. And also, for example, exercise 8, you are given the parametric representation for, let's say this is a circle, and you are also given the domain of t, the parameter is larger than or equal to 0 and less than or equal to 2 pi. What if you are only given some constraint on x? One more step is to calculate the domain of t. Okay, what's the range of t? What's the lower limit for and upper limit for calculating this integral? Okay, that's all. That's basically what's discussed in this tutorial.